Swayam Prabha. Digital India. Educated India.
Professor Kodandaraman Ramanujam. He joined the Department of Chemistry at IITM in 2011 and currently serves as the adjunct faculty of the National Center for Catalysis Research. Holding his PhD from IISc Bangalore, his expertise as a skilled electrochemist is propelling India into the future. Thank you for joining us, sir.
Okay, so how many of you from class 11? Huh? 10, huh? 12. Oh, everybody in class 11 going to 12 now. That means you might have completed already thermodynamics, kinetics. Okay, so then what we will do, since you have studied a mole concept, I will start something from there. Okay, and then from there we will build on electrochemistry that you will be studying anyway this year. Okay, so now since the board is still wet, I am not writing, let it dry. Okay, so suppose you have 1 mole of electron. What is that number, 1 mole? 6. So that's called Avogadro number, correct? So what is the charge, elementary charge of electron? So what will be the cumulative charge of Avogadro numbers of electron? Coulombs, all that you know. Okay, so if you see the charge is now related, is also a stoichiometry related to the amount of material you have. Suppose in this case, I have say lithium. So I take 1 mole of lithium. 1 mole of lithium is equivalent to 7 grams, roughly 6.9 something. 7 grams of lithium metal. And suppose I assume lithium is undergoing oxidation in the reaction. So lithium will become lithium plus 1 electron. Why it gives only 1 electron? Yes, octet rule, right? So it gives 1 electron, is easy. In fact, you can remove any number of electron, whatever the electron it has. Accordingly, you have to spend energy. So that means 1 lithium in the reaction I envisioned gives 1 electron and 1 lithium plus. That means 1 mole of lithium will give 1 mole of lithium plus and 1 mole of electron. In other words, 1 Faraday of electricity or 96,500 coulombs of charge. That is what this would give. And now, since I know the density, okay, it is 0.53 gram per cc, okay. So what I can do is I can calculate something called the theoretical capacity. Okay, what is capacity? Suppose you have a water tank at home. How will you measure the capacity of the tank? In volumes you measure liters, gallons, whatever it is, right? So that is the capacity of the tank. Similarly, in this case, the capacity of this particular material, lithium, we are defining in terms of how many electrons it has to offer, correct, no? So if I take 1 mole of lithium, it has 96,500 coulombs of charge worth of electrons to offer to you, correct? So that is called 1 Faraday, but that number 96,500 coulomb okay, I can also represent in a different unit. For example, how will you measure the length in meter, millimeter, kilometer, feet, inch, correct? Likewise, the charge also I can measure in different unit. And I am going to give you a unit which is electrochemistry like. Okay, what I am going to do, I am going to divide this number, okay, by time, okay. So what is this? This is 3600 seconds per hour that you know. Coulomb per second is what? How many coulombs flowing every second? It's a current. It's like how many liters of water flowing every second, like that. Water current, this is electrical current. So coulombs per second is ampere. So this number works out to be 26.8 ampere. R goes up, ampere R. Okay, so it's again stoichiometry. So I can say 1 mole of lithium can give me 26.8 ampere hour of electricity. I can say that because they are all connected by stoichiometry. And now you see what I have done. You can also say 26.8 ampere hour per mole. Why? It is given by 1 mole of lithium. Okay. So I can also divide the molar atomic mass of lithium, which is 7 gram. You will see this will work out to be 3.8 ampere hour per gram, and this is in milliampere hour, going to be 3828 milliampere hour per gram, correct? Yes or no? I can also convert it into kilogram if you want. So you know you have to divide by 1000 gram is 1 kilogram, you can do it. Okay. So this is what we know. But here what I have done, since I know the density, I can also express it in the milliampere hour per liter, right? So the former one, which is expressed in the unit of ampere hour per gram, is called specific capacity. It is specific to 1 gram, correct? The later one, it is in ampere hour per liter, it's called volumetric specific capacity. Per unit volume, how much is the capacity it can hold. But I have done in this slide something more. I have used some voltage, did something and all, right? So that is what is the talk of today's lecture, okay? How you get that value, where it is coming from, correct? So now let's look at, so now we know what is stoichiometry. I connected that to charge. Now what I am going to do in the second year, you will be having a chapter on electrochemistry, in which you will study something called electrochemical series, okay? Basically, you have already done in the 10th standard. Suppose if I have metals like zinc, copper, lithium, how will you organize them in the order of their reactivity? Which will come first? Zinc, copper, lithium. Lithium come first, then? On what basis you are doing this organization? You forget about electrolyte and all those things. Is there any other way by which you can order the reactivity? Yes, very good. Suppose in the first this thing, periodic this thing, lithium, sodium, potassium, how will you order them in order of reactivity? Which is more reactive? Lithium, sodium, potassium, cesium, suppose. Which is more reactive? Cesium. Why? Easy, right? In other words, cesium will give by photoelectric effect electron easily compared to the other guys. In other guys, you need to use a photon of higher in energy, correct? In cesium, it is lower in energy because the electron is far away from the nucleus. It's easy to eject them. So the one which exhibit easily photoelectric effect, what it means is using an photons of lower in energy, right, is the one more reactive. So here reactivity I am defining based on how easy to lose electron. Okay, if somebody losing electron, then that electron is available to reduce something, right? Suppose I have another species like fluorine, which is longing for electron, then what will happen? The cesium loses, the electron will land up there. So fluorine will take it up. It becomes fluoride. Okay. So basically, the example I gave, cesium you mix with the fluorine, you get cesium fluoride, is actually a battery reaction. How? Cesium is your anode here because cesium is interested to lose electron. Okay. And fluorine is interested in gaining that electron. But these two are two different energy levels, right? That's why electron is flowing from the higher energy level to lower energy level, correct? So there is a difference in energy levels from where the electron originates to where it goes, correct? In fluorine it goes to p orbital, right? So now if you look at it, this energy gap, whatever the energy in this gap, now will come out as heat. If you simply mix cesium and fluorine and shake it, and you see some heat is evolved. Why that heat is evolved? Because of electron going from higher energy level to lower energy level. So that extra energy is liberated as heat. Imagine if I have a means to convert that heat, instead of producing heat, directly produce electricity. How will I do that? Very simple. I will not let these two mix directly. I will put a wire. That wire through a resistor, I connect it to this. Okay. Now what will happen? Through this wire, the cesium will lose the electron. That electron will come through this, go through this, go through this. But we have to complete the circuit. The circuit is now C-shape. I have to make it O-shape. How will you make O-shape? Something from here should go there. Either cesium should come here to close the loop, or I should push this guy to go there. So that means I need here a medium for the flow of ions, and here I need a medium for flow of electrons. So you can use a metal with a resistor, so electron can flow, ions cannot flow through the metal, and you can put some electrolyte solution in between these two electrodes, so ions can flow. By this way I can complete the circuit. So basically I made a battery now. What is the electrolyte, what we should put, what we should not put, all the discussion different, but nutshell, this is how you construct a battery. Yes, right? Makes sense? Any questions on this? No. So now you have ordered a cesium more reactive, after that whatever it is, finally lithium you have put, right, in that series, correct? How? Based on how easy to lose the electron. Similarly, in the second year you will see something called electrochemical series. Electrochemical series tells you same thing, which is having more reducing power, which is having less reducing power, with respect to a reference. The reference is hydrogen electrode. With respect to that reference, we are going to scale the material and showing that, okay, these materials have very good reducing power. For example, lithium. Lithium likes to lose the electron, whereas hydrogen can lose electron also, gain electron also. If it loses electron, become proton, if it gains electron, become hydrate. Okay, it has two choices. But if you look at it, if you have lithium and hydrogen together, lithium will lose electron because sitting at higher energy, and the hydrogen will gain that electron. You will form lithium hydride. That's a battery again. You know, it's a lithium hydrogen battery. So the voltage that you are seeing, actually the voltage of lithium hydrogen battery in standard state. In standard state, the hydrogen battery potential, I am going to assume it like it is, what do you call, 0 or whatever it is, or some number. You will see that how we do. So actually it's a lithium hydrogen cell. Hydrogen electrode is used as a reference electrode there. Since hydrogen electrode means it's between proton to hydrogen, that moment. That means lithium will now lose electron. That electron will go to proton now. Proton will become hydrogen. So I have a lithium hydrogen cell. Okay. So now if you look at it, why should a resistor be connected? You can remove resistor, then you cannot control. If suppose you have water tank, overhead tank, you want to draw water such that in the kitchen you can wash. Alternatively, you can have a tank, open the entire bottom of the tank, let the water fall into your kitchen straight. Which one you prefer? First one. In other words, here also, I wanted to basically control the rate of the reaction. Control the how much lithium oxidizes or how much anode oxidizes, how much in the reduction happens in the cathode. I basically want to control. So it's like a valve in your water tank, okay, that pipes like that. Here I have a valve. This valve is an electronic valve, so it is a resistor. So put the more resistance, then electron will flow slow. Accordingly, reaction will slow down. If you reduce the resistance, then electron flow will increase. Accordingly, reaction rate will increase. So basically, it's a kind of a tap which regulates the rate at which the reaction happens at the electrodes. In a regular chemical kinetics, you cannot control the reaction. You take two material and mix them. If they react, then they will react at its own speed. You have no way to control it. There are some controls available, like you can heat or cool, or you can mix, or you can keep it idle without mixing. By that way, you can control. But there is no real way like the way we are doing here, a tap which can control really from outside we can do it. That is possible in battery, unfortunately not possible in chemical kinetics. Understand, no? So now we have done that. So we actually have a lithium hydrogen cell wherein lithium oxidizes one side, hydrogen is evolves in the other side. So that's a cell notation I have given here. Cell notation, what I have written itself not complete. Generally when you write cell notation, according to IUPAC convention, the reduction reaction you have to write it in the right side, oxidation reaction right to be the left side. So in case of lithium, which is oxidation reaction, lithium is going to oxidize, so that's oxidation reaction. So I have lithium metal, okay, that is dipped in a solution containing lithium ion, say it is 1 molar standard condition, and then I have something to conduct ions which I call salt bridge, okay. The salt bridge represented by the two vertical lines in your textbook. Then I have proton and is again in 1 molar concentration. Then I have hydrogen gas, it is at 1 atmosphere. That means there is an equilibrium between the hydrogen gas and proton in the solution. Then we have a platinum electrode. Okay. So when I ask you to write a cell notation, you not only write the material involved in that, you should also write the states of those material. Either they are solid or liquid or aqueous, whatever it is. So in this case, this is aqueous solution. So you write it like this. Correct, no? So you put the state of the matter, and also if it's a solution, you should also tell what is the concentration of the solution. 1 molar, 2 molar, whatever it is. Okay. So this is how you write the cell notation. Now we know if you write like this, that means there is a reduction here, there is an oxidation here. And again there is an equilibrium between these two guys. That's why there is a vertical line. There is an electrochemical equilibrium between these two. What is electrochemical equilibrium? Lithium. This is equilibrium, correct? What is the electrochemical equilibrium here? This is electrochemical equilibrium, right? That vertical line says that, indicates that. We don't need to write every time this one, okay? And this double line tells you there is a communication between these two through ions. That is called salt bridge. Now the cell is not operating. This cell is idle. It's not doing any job. Okay, there is an equilibrium separately here, there is an equilibrium separately here, and they are not connected. Therefore, there is no action. Therefore, there is no action. How will you, if suppose according to Le-Chatel's principle you have studied already? So according to Le-Chatel principle, there is an equilibrium already. If I want to disturb that equilibrium, what should I do?
Change the temperature, pressure, concentration.
Very good. If you change the temperature or pressure or concentration, what happens in the equilibrium? How it does? The moment you disturb the equilibrium, will there be a reaction or not? So, when you disturb the equilibrium, it will try to attain again equilibrium, but you have varied one of the parameter. So, how it will attain the equilibrium constant, same equilibrium constant? It backward, depending upon how you disturb. To move forward or backward, you have to do, there should be a reaction happening. There should be certain moles of A going B or B going A, something should be happening in the A goes to B reaction, right? So, if you look at carefully, to attain another equilibrium, basically there should be a reaction. Reaction means there should be exchange of electrons, correct or not? If there is a reaction between lithium and proton, lithium will be losing electron, proton will be gaining electron. That's the reaction that's happening to when you disturb the equilibrium between involving the lithium, hydrogen, proton, lithium plus solution, right? That's what will happen. Same here. Now I can disturb the equilibrium here because why? I have an equilibrium, it's a half cell. Why it is half cell? Because I am not telling where this electron goes. That's why it is half cell. This is an half cell because I am not telling where this electron will go. Only if I show the cell, you know this electron comes from here. This is the same electron here goes there. Okay, but if I don't give only half cell, if I give, you will not know because I don't know what's going to, because with which electron I am going to couple this. I have no idea. Correct. So now if you see, we have two half cell, they have independently an electrochemical equilibrium. Now the moment I connect this to this electrode, okay, the moment I connect this to the other electrode, what happens? The potential of this electrode and the potential of this electrode are now meeting, correct, no? When I meet, what will happen? There is a way. It is like I have a tank, two tanks, one is at lower head, other is a higher side. Now I put a pipe connecting them and put a valve to close them. When I close the valve completely, so the water here there, that means it is at equilibrium because the level of the water doesn't change. And whatever water is here, it is still there and its level does not change because it is in its own equilibrium. The moment I open the tap, they are not keeping quiet, automatically it flows. Why? Because there is a gradient in potential energy which is caused by your gravity of the earth, therefore it goes. So there is an invisible force which is acting on the material, that invisible force is gravity, therefore the water flows. Similarly, in electrochemistry, there is an invisible force. That invisible force we call potential. So, if there is a potential difference, automatically electrons will flow, correct? So, that means what? The potential at this interface, not going to be same if you see electron is flowing in the circuit. If I put ammeter in the circuit and I can look at whether there is a flow of electron, if I see ammeter showing some reading, it means the potential here and potential here, electric potential there and electric potential here are not the same. Therefore, you see a flow of electron depending upon which side the slope is there. The gradient in which side, accordingly electron will move. Okay. So, just because I put a half cell this side, that half cell that side doesn't mean always cathodic reaction will be that side. That is cell notation. But when you make a cell, if you keep the cell like this, it will not change the reaction. It will be still the same because the gradient only matters. It's not how you write. Just to follow a convention, we write it like this. Okay. So that we can define E cell. E here is not energy, here voltage. E cell can be defined as a potential at the right hand side minus potential at the left hand side. For that, you have to follow this convention. Okay. If this value happens to be positive, then it is a galvanic cell. What is galvanic cell? Delta G of a reaction is less than 0. According to thermodynamics, what do you call that reaction? Spontaneous. So, electrochemists don't want to use that word. We call galvanic. If something spontaneous, we call galvanic cell. So, that means if delta G greater than 0, you call it as a spontaneous, then non-spontaneous, right? We call it as electrolytic. Okay. So, we say it's an electrolytic cell. It means what? I have to spend energy for the reactions to happen because it's not spontaneous. Naturally, it won't happen. I have to invest some energy for the reactions to happen. It is like pumping water from the sump to overhead tank. It will not happen automatically until unless some giant earth comes near earth and applies gravity in the other direction. Then the water goes like this, everybody go up. I mean, see, if we look at it, right? So, there should be a gradient for the charges to flow. Okay. And you can see it can be a galvanic cell or electrolytic cell depending upon the condition. Okay. What is the condition? Conditions, many things here, pressure is there, solution concentration is there, so many things can change. Therefore, the conditions, therefore the potential of the electrode can change. But I have not still taught you what is this potential, where it is coming from. That we will reserve for some time. Okay. So, now I will teach you how we can construct a concentration cell, because now you know what is this galvanic cell. Galvanic cell is a spontaneous process, electrolytic cell is a non-spontaneous process. Now, there is something called concentration cell. It can be galvanic or electrolytic, okay, depending upon how you write it here. If I write it here, then E cell comes positive, then I will, the way I have written, I can call it as a galvanic cell. But you see what is concentration cell? Very simple. So, to determine, we are going to use this equation. You know this equation. What is this equation? So, equivalent of that in electrochemistry is okay. For a half cell, it is written like this: E equal to E naught standard potential minus RT by NF, okay, number of electron involved in that reaction, ln reduced form of the species in that equilibrium, then oxidized form of the species in the equilibrium. Okay. If it is a full reaction, you will use this, that means product concentration divided by the reactant concentration. If it is a half cell, reduced form of the species up, oxidized form of the species down. Okay. So, you will be using this is called Nernst equation. So, you will be studying this Nernst equation also in the +2. Okay. Now, what we do, I wanted to set up a concentration cell. So, I have platinum and hydrogen electrode and proton, and I have a salt bridge. Say this is 1 molar, say this is 1 atmosphere. I have again a cell, because it is a concentration cell, 0.1 molar, hydrogen, 1 atmosphere, platinum. Okay. Clear? Now, if it is a galvanic cell, suppose, galvanic cell means spontaneous reaction. One side there should be anyway. automatically there should be a reaction going. Obviously, this can be a galvanic cell, but I don't know because the cell notation is something E cell is equal to E right hand side, E left hand side, right? So if you look at it, let's not go into the equation first, let's think for a second. What is different here? Concentration. So if this fellow automatically heading to an equilibrium, then what it will do? It will try to balance the concentration. How it can balance? Because this is an electrochemical cell, we cannot mix a solution and balance. It has to do some electrochemical reaction. So that means I have to reduce the concentration here, increase the concentration there, correct? If I have to increase the concentration here, what reaction should happen at this interface? Reverse. So it should oxidize this to this, correct? That means now if it is an electrolytic cell, automatically oxidation happens there, correct? No? But in the standard notation, how you should write? On the right side, whatever is there should be a reduction reaction. So I have written opposite, correct? No? Right. So this I am telling because just because I am writing like this or making a cell wherein I put the one chamber in the right side, it doesn't mean automatically it is a cathodic chamber. Not work. Okay. So now if you look at it, to decrease the concentration here, what should happen? Reaction go this way, right? This is reduction, okay. So basically to act as a galvanic cell, there should be an oxidation here and reduction here, but I have written the other way just to put it in the cell notation. So according to the cell notation, what I should expect here? Reduction, here oxidation, but that against the natural process, right? That means the way I have written this is a what cell? It's not wrong. What cell? Electrolytic cell. It cannot go wrong. You can write the way you want, but you have to specify with some label. This is the way I have written. It's an electrolytic cell because by definition I wanted to have reduction in the right side. But you can just apply your logic and check. Oh, for this reaction to head to the equilibrium, the concentration has to equal. In that case, the right side reduction cannot happen. It's only oxidation that can happen. It's very simple logic, but I will prove it through Nernst equation as well. You will see that, okay. Now what Nernst equation tells, this is what it tells. So E right hand side minus left hand side. Now E naught is here also, E naught is here also. The E naught will get cancelled, so I am not writing that part. Then it's going to be for this part, right hand side. So minus RT by NF ln, reduced form here is hydrogen. Hydrogen partial pressure is 1 divided by oxidized form is proton. The proton is in concentration 0.1, correct now? And then minus of minus becomes plus RT by NF ln 1 by 1, correct? Because the concentration is 1. Now let's work it out. Ln 1 is how much? 0, this fellow will be 0. Then I will have this. This will be some 10, ln 10. Then it will be 2.303 by RT by NF ln 10, that becomes 1. So this, all of them are positive numbers. They are constant basically, okay. E cell is now negative. Delta G will be, what is the relation between delta G and E cell? This is the relation. Then this will be electrolytic cell. So it's correct. That's why I have to follow the sign convention. That be in sync with the thermodynamics. Otherwise it will not be in sync with thermodynamics. But I know one thing. If I have to decrease the concentration here further and increase the concentration here further, then I have to do only electrolysis. Only if I do electrolysis I can get to that. Correct, no? But if I want to equalize the concentration both sides, I cannot do electrolysis. I have to make galvanic cell. That means I have to let the energy come out of the system. That means electrical energy will be generated in that process. So you will get energy. In that process, they will become equal. Make sense? So this is how you make connection to the electrochemistry and the thermodynamics. Clear? Any question? plus no, galvanic means spontaneous. So 0, right? But you always have this convention, how should I write? Whatever the way you write, when it comes for writing, you have to be obeying the IUPAC convention. And you have to use whatever the steps given. In that way, if you look at it, it is an electrolytic cell. Okay? But if it is an electrolytic cell, what will be happening? The concentration difference will be further increasing in this case. Yes, sir. But if you want that concentration to be equal, then you have to run the cell like a galvanic. In that case, what you should do? You should not use any external energy. You should just put a resistor and connect the circuit. Energy will come out, concentration will get equal. So, if you wanted to write it as a galvanic cell, what you do? All you have to just swap and write it. If you swap and write it, automatically E cell will come positive. Then the way I have written, it's a galvanic cell. But it's a concentration cell, but it's a galvanic cell also, right? Very good question. Any other question?
Why do we use F in this equation?
Where is F? Very simple. Delta G is NFE, right? You substitute, bring the NF down.
What is the F?
Faraday, right? See, what is energy? Energy is charge that is moved under a potential. So, charge into voltage is energy. So, if you look at here, it is the same thing. This is actually charge, N and F. This is voltage. Charge into voltage is energy. Electron volt. Electron charge into voltage, right? Same thing. If you forget, you remember electron volt, then you get this equation in your mind. Correct, no? Right. So, the other question was, why we use platinum? Good question. So, what is this electrode called? They are not telling platinum electrode. Correct, no? Platinum is there, but you don't say it's a standard platinum electrode. You are calling it standard hydrogen electrode.
Hydrogen is being oxidized or reduced. Hydrogen is electrode.
Then why platinum? Put some stainless steel, put some nickel. Put gold. Platinum also equally expensive, right? See, what is reactive all depends on what is the environment in which you are putting. What is reactive in Earth need not be reactive in another planet, because your atmosphere will be different. Correct, no? Silver we are heavily using here. Can you go to what do you call that? The Guru planet? Saturn. Wherever the planet, that planet has got sulfur atmosphere. Venus, wherever it is. So, you take your silver plate which you are using for eating, go to that planet and try to eat. Will you be able to do? So, it is silver less reactive here, becomes more reactive there. So, it all depends on the atmosphere in which you keep material. When you will get angry, again depends on your atmosphere. The same person is good, bad, depending upon which atmosphere you are put in. You understand? No, always there is a reaction under the influence of a force. It is not going to happen on its own. If you are on its own, you are acting means you become this, right? Then only on its own you will do angry or laughing or beating or something, right? Right. So, now clear? Now platinum, why platinum? And if you are putting platinum, why are you not calling platinum electrode? Okay, and again it is not just platinum, it is what? That platinum has a special name. Yeah, it can be used, right? But why we are not using? That's the question now. So, it is not simple platinum. What is this platinum? In the textbook, if you have read, it's called platinized platinum or platinum black. Platinized platinum, or it is called alternatively platinum black. How platinum black is different from the platinum? Coated with what? Tar? If it is coated with palladium, I should have written platinum coated with palladium, then hydrogen, then this. But I have not written, I was still writing it is PT. That means platinized platinum is also PT. Platinum black is also PT. But how are they different from the platinum?
Platinum or palletized platinum?
Platinized platinum. Palletized
Sir,
no.
why are you putting platinum on platinum, sir?
Think about it. You don't ask me, think. Huh?
Electrons, something, sir, anything that makes it reactive.
Then it is not neutral. It will be platinum positive. Right? Then it should be PTC. You are saying that the crystal structure of the platinum is different. Okay, good thinking, but it is not.
So just if the H2PR 7 solid phase is that the same thing? It maintains like electrical.
Okay, kind of. Okay, platinized platinum means you know the gold. The
It highly absorbs hydrogen.
yeah, it highly absorbs hydrogen. Why it highly absorbs hydrogen?
So it keeps current flowing, sir.
Hmm?
It keeps current flowing, sir.
No, it cannot be keep flowing. You for a reaction to happen, cell has to be complete. Only with half cell will the current be keep flowing. Not possible. If it's keep flowing, then platinum will bulge with something. If it takes electron, the platinum will be full of electrons. That's not possible, right? It's like a sponge you are talking. So he gave some partial answer, but I'm asking why it should absorb more hydrogen. You have to think.
For the backward reaction, sir.
No, it's in equilibrium, right? So at that, once you dip platinum into sulfuric acid or HCl, there is an equilibrium established. Initially reaction goes in one way, immediately it comes backward, then there is an equilibrium. Okay? It happens in a fraction of a second. Now you are right, it absorbs more hydrogen. Why should it absorb more hydrogen?
But it has a less density, or it fits in the hydrogen molecules fit in the intermolecular spaces.
No, it is not. It is only happening in the surface, so it's not diffusing inside bulk. Yeah.
Maybe the hydrogen dissolves in water to take it out. There's no water. There's no water here.
There is water there, aqueous solution, but see, answer is the following. You have a gold, right? Gold chain. It is yellow in color. Have you seen gold in any other color?
Yes, sir. Purple.
How? Only with the gold. You should not mix anything else to the gold. Okay, you react with aluminium.
He's asking pure gold.
Pure gold, have you seen any other color? No. Okay, you have not read about nanochemistry? No, okay. See, if you take a gold particle which is metallic in nature, correct? Metallic in nature means what? The valency band, conduction band, either they overlapped and had a partially unfilled state by which electrons can move, or you have a partially filled valence state and things like that.
Like gold can also appear in black, right? When you
Yeah.
create microscopic particles, those
Ah.
chemical reaction.
Yes.
Because light bounces around everywhere.
Yeah, good. Good. So, the gold is yellow. You start dividing the gold. What was metallic? Okay, why it is metallic? Because there was a valence and conduction band, they were overlapping. Okay, as you keep on dividing, what will happen? That overlap will decrease. And the gold will slowly turn into nanoparticle. Then color will start changing because the color comes from the electronic transition between these levels. Further divide the particle, the gap will widen, may become semiconductor also. Then further divide, the gap will widen. So, same gold, depending upon how the band is structured, its color will change because what light it absorbs, what it emits, or what the complementary color comes out of it is different. Correct? Therefore, the gold, if it is in ingot form, it is in this color. But once you start reducing its size, its electronic structure change, therefore its color will change. So, platinized platinum is nothing but a nanoparticles of platinum deposited on platinum. So, it's called platinized because you are depositing platinum on the platinum. And that is a nanoparticle and whose color is black. So, it is platinum black. Why we do? If you do that way, your surface area will go up. Why? Instead of an atomically smooth surface, you start throwing very tiny nano balls there and then you look at in the microscopy, you will see there is a lot of terrain valley kind of thing, right? So, the overall surface area in a given geometric area will increase. More area means more interaction between the hydrogen that dissolved in water or acid and the electrode. So, more hydrogen will absorb on the electrode. So, more catalysis. reaction will be fast. Alright. So, platinized to platinum, basically what happens is the following. So, the platinum and hydrogen which is in the aqueous phase react to produce PTH. So, now this will either oxidize, if it oxidizes it will produce okay. So, this is a reaction, this reaction goes through this step. So, it is a hydrogen electrode. Why? Now hydrogen is on the electrode, okay. Hydrogen gas cannot be electrode, you need to have someone who can absorb hydrogen, okay. So, how something will absorb? So, hydrogen will not absorb in each and every material you will see. Wherever energetics favors, there only hydrogen will absorb. Have you studied absorption, desorption, isotherms? Maybe in the next year. Huh? Okay, you will see maybe this year. Okay, so it will not, any metal will not absorb on anything, right? No, there is some energy interaction between them. If that is favorable, then they will absorb. Therefore, even though a gold, silver, all that available, we will not use it here, because hydrogen easily absorbs on platinum than on these materials.
So, other than surface area, what criteria matters for the rate of absorption? So, because for example, here we have platinized platinum. So, you could technically have goldized gold.
That's what I am saying. Energetics has to favor for the absorption of hydrogen.
So, how do we calculate
Then why not platinized gold or something like that?
Okay, you can use.
We can use.
Yeah, you can use.
So any metal platinized. So so then platinum is expensive. They can use some platinized copper or something.
You can use, these reactions will happen, but the potential will not be the same. That means you cannot call it as a standard hydrogen electrode. It is an hydrogen electrode with a potential different than the regular hydrogen electrode.
It will just be a little more, less.
That depends on what is the metal you are using to coat platinum. See, you should look at this way. If I bring any two different metal and put it together, what is happening at the interface? What do you think will happen from your physics knowledge? Suppose I have a metal which has a lower work function and a metal with a higher work function. What is work function? The difference from the vacuum level to the topmost energy level, right? So, a metal with a lower work function, a metal with a higher work function, I am bringing them in contact. What will happen at that interface? From where to where?
Lower work function to higher work.
Correct. Then this side of the metal will gain positive charge, this side of the metal will gain negative charge. Whenever you have a charge separation in a given region, what will develop? Potential will develop. So, now earlier I am going to, also you see this is between two metal. You can have this potential developed also if you have an electrode and an electrolyte. Because electrolyte has got a redox energy level, electrode has got a Fermi level. So, if the Fermi level is higher than the redox energy level of the solution species, Fermi level, again in the physics you must be living. So, Fermi level is the topmost level in which you will find electron in a given material. So, kind of, yes. So, because the valence electron and all we will say for the element, but when you come to the metal, it is a collection of many atoms of that element. So, you will not have a atomic orbital, you will have a band. So, top of that band is Fermi level. You understand? If you are talking about single atom, you can talk about valency cell, all these things. Now, you have to talk about valency band, conduction band, right? So, in the topmost level where you find at a 0 degree Kelvin, okay, because at higher temperature what happens, there is a chance for the electron to go to the higher energy level, correct or not? If you take an element, put it at 0 Kelvin under different temperature, you think everything will be same, it won't be same. Because you are not putting single element, you are putting Avogadro number of that element there and then you are looking at it. So, if you look at the electron, where the electron is, the last electron, not necessarily it will be there where as we write in the Alpha principle, that orbital can be little higher also. Why? Depends on whether it got any extra energy, so the electron jumped and things like that. There will be a distribution of energy, right? There is a distribution of velocity of those particles which are moving in the gas phase, correct? So, we will come to those things later. Okay. So therefore we define a temperature 0 Kelvin, therefore we are not giving any energy. So the atom we are taking and putting it there without giving any energy. Therefore at that condition where the electron is there, in its ground state, at the top of that state where you find the electron, okay, that energy level is called Fermi level in case of a metal. Okay. So because single atom means it will be like then orbital where you find. If it is a collection of atoms, it becomes a band, then the top of that, the topmost point in that band where you find the electron is the Fermi level. Okay. So now you have Fermi level. So your work function you define from the Fermi level to the vacuum. Okay. Now you have electrolyte, it has its own redox energy and you have a Fermi level. Now you bring them together, what will happen? If it is this way, electron has to come from here, from the electrolyte. That means electrolyte will undergo oxidation. Or alternatively, metal can undergo oxidation, leaving the electron back here. So the energy will go up. Right? You lost metal into the solution, but the electron which is metal left is basically the whole metal. So now the extra electron will go to the next energy level. Therefore, the energy level of your metal will rise now.
Can you explain that again little slowly?
Which one?
Get the last one.
The last one?
Yeah, this last.
Suppose I have, this is vacuum level, okay. So I have a Fermi level of a metal, okay. So this is my work function, okay. Now I have another metal, so this is metal A, I have another metal, metal B. Then if I bring them together, then what will happen? Because this has got higher work function than this, right? So electron will flow from here to here. So positive charge created here, negative charge created here, therefore a potential generated. Same way, if I have an electrode with a Fermi level here, and I have an electrolyte, this side of this is a metal, okay, whose redox energy is here, redox potential or energy, whatever it is. So redox energy is here. Then what will happen? Electron will flow from here to here. Then you will generate positive charge here, you will generate negative charge here. Correct, no? Yeah, now electrolyte cannot undergo oxidation because the electrolyte energy level is lower than this. Now imagine it is opposite. Fermi level is here, this is the interface. Your electrolyte redox energy is here. This E here is energy, not voltage. So now what will happen? There are only two ways. One way is this fellow lose the electron to this. That means your electrolyte undergoes auto oxidation. In that case, you will have net positive charge here, negative charge over here. One other way is the metal oxidize, leave the electron back. Metal dissolve. Suppose it's a zinc. Zinc will dissolve, become zinc 2 plus, go into the solution. Now you had N zinc. Now you have only N minus 1 zinc here. 1 zinc went into the solution. So now this extra electron left by this zinc, which how many? 2 electrons will be in the metal. So this will raise the energy level because you are adding electron. When you add electron, where it will go? Wherever the vacuum level is there, empty level is there, there only it will go. Virtual orbital only it will go.
Yeah, but so the case one also the energy, the Fermi energy level will change, right?
Where?
So the
Yes. Everywhere Fermi level will change as a result of this interaction. Basically, they are heading to a Fermi level equilibration.
yeah, that's what I say.
It's like if you have two water tank of different level and you connect them, what will happen? The level automatically will adjust such that it is equal in both sides.
Sir, but like the first case will be more favorable because net energy is lower, right? So it will result in more stable conditions.
Where? First case?
Two cases, right?
This one or this one you are talking?
Down, up and down.
Hmm.
Yeah. So that first case, that case will be more preferable than the lower one.
Now you cannot say that, how will you say? I have not told you the system. Okay. See, certain reactions, any reaction you take, it will not happen just like that. In kinetics, you will study a reaction will happen having something called activation energy. Okay. Suppose I have two reactions whose reactant and product are almost at the same energy, but they have a different activation energy. Which one will happen first? but almost energy wise both the reactant here is different from the reactant there, but their energies are roughly same. The product here and product in the other reaction, they are different product, but their energies are roughly same, but their activation energies are very different. Therefore, one will happen fast, one will happen slow. So, what I am trying to tell you is, you can't make this guess until unless you know what is the system. Only if you know the system, you know what is the activation energy involved.
Yes, sir.
Then only you know first one is preferred or second one preferred. In other words, among these two, one may be having higher activation energy than the other. So, whichever has the lower activation energy, that pathway your system will choose.
Depends on the activation energy and not the energy of the particle.
Yeah, energy of the particle important for the flow of charge, but activation energy is also important. That determines the rate of flow of charge.
So, how do we calculate activation?
Those are all, I am not planned for teaching that here. Activation energy you can calculate, chemical kinetics will be there in your +2, you will see that time. It's a temperature dependent phenomenon, they will plot the rate of the reaction with the temperature and then they will estimate from the slope the activation energy, okay. That you will study in +2, okay. Right now we cannot pack everything in 1 hour. So, I came with the aim of teaching you electrochemistry, okay, right. Clear? Any questions so far? Now you know what is stoichiometry, how we are connecting to electrochemistry. You know the thermodynamic equivalence, that is what is a galvanic cell in thermodynamics, electrolytic cell in thermodynamics, correct? And you know how to convert your the other equation into a Nernst equation, okay? Using the Nernst equation, how will I calculate E cell? From there, how will I say the way I have written is depicts a electrolytic cell or concentration cell, you will know that, correct? And then we also understood why there is a potential generated at any interface. So, a good question that the platinum under is expensive, why don't you go to platinum on gold? Yes, you can do. Then you will have a potential drop between gold and platinum and your voltmeter will measure including that. So, even though you are still doing the same hydrogen reaction, but the potential you are going to report going to be different. But that is not a standard hydrogen electrode. By definition, standard hydrogen electrode is the one which is wherein the electrode is purely platinum coated with the high surface area platinum dipped in the 1 molar acid under 1 atmosphere hydrogen pressure. If only under that condition, whatever the potential generated, you will be using it as a reference in measuring the potential of other electrode electrolyte interfaces that you are going to generate. Because I need a reference to scale other electrode electrolyte interface to claim whether that particular interface is more reductive than the reference interface or it is more oxidative than the reference interface, which I need to do, because that is where we discussed the concept of lithium, sodium, potassium, cesium. How will you do the reactivity ordering? You gave some order based on some concept. Similar in electrochemistry, I have an ordering based on this how interface is reductive or oxidative with respect to a reference. But that reference is going to be standard hydrogen electrode. By definition, standard hydrogen electrode is you have to use a platinum only. You can't use any other metal and coat the platinum on that. You can do, reaction will happen. That's practical thing. Practical thing is different. Measuring standards is different. Practically, you will think this way only. Oh, platinum is so expensive. Why should I make a platinum wall? I will make a wall with platinum coating. Like in the temple, no? They will say this is gold this thing. But it is not gold. It's actually copper coated with gold. Correct, no? So, then only it is a, cost effective. They want to have a gold look, but actually they are not rich inside. You understand, no? These are all like people, some, an old Tamil movie used to be there. You will have an iPhone cover with the Android phone inside. Like that. They wanted to look rich. Okay, that's jokes apart. Any other question? We are completing 1 hour.
Swayam Prabha. Digital India. Educated India.